Okay. Do you see the slides?
Yeah. Yes, I can see that.
All right, perfect. Okay, well, thanks again. Yeah, I'm very excited, pleased to have been invited and excited to be talking about mortality forecasting together with you. So let's start straight away. So why mortality forecasting? Well, mortality forecasting is a topic that I believe is very relevant, not only for academic research, but more especially for social policy, for informing public policies, and so on. In particular, mortality forecasting is important for assessing the sustainability of future pension schemes, insurances, elderly care, but also to predict the future course of population aging, to project populations, and so on. The field of mortality forecasting has experienced revived interest in the most recent years, especially thanks to the seminal model that Lee and Carter introduced in 1992. So for those of you who are not familiar with this model, this is a very elegant and rather simple model that allows one to describe a matrix of log mortality rates, log ln-mxt here, using only 3 sets of age or time-specific parameters. So we have alpha x that captures the shape of mortality over age, kappa t that captures the level of mortality at time t, and beta x that is the rate of mortality improvement or the responsiveness to the changes in mortality at time t. And one of the main reasons why this model got so much attention and became so popular was that a fairly complicated problem of forecasting several time series of different mortality rates at different ages basically was reduced to the extrapolation of a single time index, kappa t, thereby simplifying greatly the forecast of mortality. To put it in the words of Adrian Raftery, the model simply revolutionized the probabilistic mortality and population forecasting. And in the last few years, in the last couple of decades, subsequent literature highlighted that the model suffers some limitations, and some extensions were proposed. But as of today, the model still remains the benchmark approach for forecasting mortality, as it is used widely by statistical offices, international organizations, and so on. And last year, it was the 30th anniversary of this seminal model, and me and Giancarlo Camarda and at the booth, we wrote a comprehensive review to try to celebrate this excellent model. But today I would like to talk about different, not only Lee Carter per se, but I would like to talk about 3 main points. First of all, I will talk about the project that concerns the forecast of age-at-death distributions. I will then move to talking about forecasting mortality from a cohort perspective within a Lee Carter framework. And finally, I would like to conclude on giving my thoughts or my view on what would be, in my eyes, the future of this fascinating field of research. So starting from the forecast of age-at-death distribution, this is a project that I worked on during my PhD with my ex-supervisor, now colleague, Carlo Giovanni Camarda from INED. So a little bit of motivation. Generally, when we try to forecast mortality, we employ models that are generally based on mortality rates. And as we know, human mortality can be studied or analyzed with 3 different complementary functions: the hazard, the survival, and the probability density function. In other words, the MX, LX, and DX columns of the life table. Interestingly and importantly, these functions are complementary in the sense that if we know only one of these functions, doesn't matter which, we can derive the other 2 without the need of any additional information. And each of these functions provides us with interesting insights on the development of mortality over age and over time. So for us, it was a little bit puzzling that basically all models were based on mortality rates, and very little attention has been paid to the age-of-death distribution as a mean to try to model and forecast the development of mortality. But let's have a look visually at mortality developments. For example, here I took Danish females aged 30 to 110 and plus. We have log mortality rates. And the animation shows us how mortality has been improving during this time period. We can see how the curve, the age pattern of mortality has been shifting downwards, corresponding to improvements in mortality at practically all ages. And we can see that mortality improvements have been faster, for example, at younger ages, and maybe less fast at older ages. This is very informative, but what if we change our perspective and we look instead at the age-of-death distribution? Well, here it comes. This is the evolution of the age-of-death distribution for the same population over the same years. And what we can see is that the distribution of deaths has been moving to the right. So there has been shifting of the distribution. And at the same time, there has been a compression. So the variability of the distribution reduced. So simply by this exploratory analysis of the life table, we can see how looking at the age-of-death distribution might provide us some important information on mortality development that perhaps we cannot catch at the first glance by looking at mortality rates. So with Giancarlo, we said, okay, let's try to formalize this. Let's try to come up with a model that can allow us to model the change in the distributions over time. So a little bit of notation, let X denote the age. Let's take two distributions, a distribution F, that is a standard distribution, or a reference distribution that will remain fixed over time. And let's take any observed distribution G. And our goal is to find a transformation function T that depends on age and on a set of parameters, theta. And in particular, we want that this transformation function allows us to move from F to G by transforming the age axis of the standard. So basically, we take our standard, we reevaluate the age axis of the standard on a warped transformed axis, and we obtain an observed distribution. And after some experiments, we found that a parsimonious and a flexible way to operationalize this transformation function was this form, using a segmented transformation function that gives the name to our model, STAD, that is a segmented transformation age-of-death distribution model, which basically depends on three parameters, S, BL, and BU, which I will explain you in a minute. So looking at the transformation function by itself probably gives us very little information of how the model works. So let's have a look at graphical representation, which I think it's easier to catch. So let's take a standard distribution in black with a transformation function that is a one-to-one for now. And let's start from a simple case in which we want to describe a simple shift of the distribution. Well, in our model, we set a parameter S that is equal to the difference between the two modal ages of this distribution that basically allows us to move the standard distribution along the x-axis. And what we are doing is basically we are reevaluating the standard distribution on a new age axis that is shifted by an amount of S. So for example, if the old age 50 of the standard distribution now is the new age 60, that is 50 plus S. So we are shifting the entire distribution by 10. So we are basically reevaluating our original standard distribution on a shifted age axis. And clearly you can imagine that by changing the value of the parameter S, we are able to shift the distribution as much as we want along the age axis. However, in reality, things are never so easy, as we have seen before. So we need to model and capture also changes in the variability. And that's where the BL and BU parameters came in. So these two parameters capture the change in the variability of the distribution before and after the mode. So BL regulates the variability before, BU the variability after the mode. And in this case, we took a BL that has a slope greater than 1. And if you see the purple line before the mode, we have a compression of the variability. On the other hand, we chose a BU that is lower than 1. And if you see the purple line, we have an expansion of the variability after the mode as with respect to the standard distribution. And once again, by changing the values of these two parameters, we are able to capture a wide variety of changes in the variability of the distribution. Finally, by putting all the ingredients together, we obtain a model that is pretty flexible, but also parsimonious, that allows us to capture mortality developments over age and over time. Very well. So now the question is, how do we estimate the standard distribution? Let's take two observed distributions, G1 and G2, as depicted here. And perhaps a naive approach would be to take a simple mean of these two distributions. This is what is shown on the left-hand side. And as you can see, the resulting standard distribution has a rather strange form that is not really representative of either of the two distributions. So after some experiments, again, we found that a better approach to choose the standard distribution would be to first align the distribution so that they share a common modal age, performing a landmark registration approach that is usually done in functional data analysis. And after aligning the distribution, if we now compute the the mean of these two distributions, or more distribution, you see that we end up with a standard distribution that is much more representative of the two original distribution. It has a sort of average variability between the two and so on. Okay, so let's try to see how the model works with real observed data. Let's take observed death counts and exposures for females in Denmark aged 30 plus here. And we start by smoothing the data so that we are able to apply a continuous model, such the one I just described, to discrete observed data. And in particular, smoothing also allows us to derive the modal ages at death of the distributions and an estimate of the parameter S. Next, for each year that we consider, we estimate the compression parameters BL and BU by using maximum likelihood, assuming that death counts are Poisson distributed with expected value equal to the product of exposure and the force of mortality. In order to forecast, we estimate the 3-time series for the 3 parameter. We select the best ARIMA model that describes their behavior, and we forecast them in the future according to these models. And we then derive prediction intervals using a residual bootstrap approach. Okay, here is the application. So we start by smoothing the data. On the left-hand side, you can see the smoothed distributions. On the right-hand side, the corresponding smooth log mortality rates. We start by aligning the distributions on the left so that they have a common modal age at death. And we estimate our standard by taking the average of these distributions. From the standard, we can then estimate the compression parameters, which are reported here. So on the left-hand side, we see the shifting parameter that in red that increases over time, corresponding to the shift of the distribution to the right. And on the right-hand side, we see the compression parameters. For example, in blue, we have the BU, so the variability above the mode. which, since the parameter is increasing, correspond to a compression of the distribution above the mode, while the BL parameter is first declining and first increasing, corresponding to first an expansion and then a compression of the distribution. Before looking at the forecast, here are some goodness of fit checks, if you like. We look at observed life expectancy at age 30 and lifespan variability at age 30. The points are the points observed in the data, the estimates from the data. We start by fitting the Lee-Carter model to the data, and the results, the fitted results are shown in red. And we can see that the Lee-Carter is usually doing fairly well in terms of life expectancy, but it's greatly misfitting on the shape of the distribution. On the other hand, our model in blue provides more accurate estimates of both summary measures of mortality. We now move to the forecast. We simulate, in this case, I think 1,000 future pets of these parameters using the best ARIMA model. And from each of these parameters, from each of these future pets, we are able to then reconstruct the future mortality surface from which we can compute summary measures for the future. So, for example, here we start again life expectancy and lifespan variability. In red, we have the Lee-Carter forecast, and in blue, we have the forecast from our approach. We can see on the left-hand side that our life expectancy forecast is greater, signaling more optimism. And on the other side, the lifespan variability forecast is lower, signaling that the distribution is more compressed. Let's have a look at the results in terms of forecast death rates. So on the left-hand side, we have the observed and the forecast rates from our approach. On the right-hand side, the observed rates and the forecast from Lee-Carter. We can see that our approach provides a nice a nice diversification of the rates, while we see several crossovers derived from the Lee-Carter forecast, which can also be observed by looking at the age pattern of mortality in the future. So you can see on the left-hand side that our forecasts in yellow are smooth, while there is jaggedness and erratic behaviors for the Lee-Carter forecast, which for some ages look particularly implausible, such as the rate at age, I don't know, 105 being much smaller than at age 95 or something. We performed some out-of-sample validation to make sure that our methodology is indeed more accurate in terms of both point forecast as well as prediction interval accuracy, which can be found in the paper. And we have already extended this model to cover, so what I presented here was only for adult mortality from age 30 onwards. We already extended the model to cover the entire age range, so starting from age 0, and also to forecast cohort mortality. And as an outlook, we are planning to extend this work to analyze and forecast co-specific mortality, and also to come up with a coherent approach to forecast mortality for a group of subpopulations. Okay, so this concludes the first part, work that I presented. I would like now to change gear and analyze instead a second project that is called Lee-Carter Cohort Mortality Forecast. Again, joint work with Giancarlo Camarda. And this is, unlike the first project, this is very much work in progress. So even more, I would really appreciate any feedback or comments that you might have. So some motivation again. As I previously mentioned, recent years have seen the proposal of several extensions of the Lee-Carter model to try to address some of its limitations. such as the jump-off bias, the assumption of normality, the fixed pattern of mortality decline, and so on. However, we didn't find applications of the Lee-Carter model to try to forecast cohort mortality. One notable exception here is the model by Haberman and Renshaw, in which cohort improvement factors are forecast, although the authors still work in an age period framework. And why cohort forecasting? Well, usually when we want to answer important or relevant and timely demographic questions related to mortality, such as what has been the impact of the COVID-19 pandemic on our life expectancy and so forth, what we would do is we would take a period perspective. We take a standard period life table, and we find out, for example, that life expectancy at birth has declined by XX years. Okay, that's super relevant, super important, and all good. However, when we work with the period life table, we always have to remember that we are working with a model. So we are hypothesizing that our synthetic cohort will live throughout the rest of their life using being subjected to the same constant mortality, age-specific mortality rates. And we know that this is a very unrealistic assumption, in that mortality has been improving over time throughout the last couple of centuries. On the other hand, when we look at cohort life tables, we don't make any assumption. We take a birth cohort and we follow this real birth cohort throughout all of their life until they are extinct. So we don't make any assumption, and we are actually investigating what has really happened to this real birth cohort. So I'm not saying that cohort analysis of mortality are more important. I'm just saying that they might provide some additional insights on mortality analysis. Why we don't have so many studies with the analysis of cohort mortality? Well, clearly because we don't have the data. So if we want to know what is the cohort life expectancy for those that were born last year, well, we need to wait 100 years or more until this cohort is completely extinct, until all the members of the cohort died out. So, and we don't have time often to wait so long. However, there is an alternative, which is we can try to complete the mortality experience of this partially observed cohort using forecasting cohort mortality forecasting. And interestingly, in the literature, there are really few approaches to forecast cohort mortality. But let's have a look again visually at the problem here. So this is a standard age period Lexis diagram where each cell in this rectangle corresponds to a particular death rate in log scale here for a given time and a given age. This is what we know and what we are accustomed to see. However, I want to move from this perspective to the age cohort Lexis diagram perspective. And you can see that age cohort mortality data come into a rather different fashion. So we have a parallelogram in which for only few cohorts, we have full data, full information. So for the cohorts from the 1900 to the 1920, we have full information on mortality rates. And from 1920 onwards, mortality rates data are available in decreasing fashion. So for the first cohort, we observe until age 99, the second cohort until age 98, and so forth. And similarly, for the cohorts before 1900, we didn't observe, for example, age 0 for the 1899 cohort, and increasingly so. So the problem here that we want to address is to try to complete the mortality experience of the most recent cohorts. And in the literature, there is probably the state-of-the-art approach to do this is what we call the Lee-Carter diagonal approach. And today I want to talk about two proposals that we make, that are the cohort and the linear Lee-Carter approaches, which still sit within the Lee-Carter framework. So let's start from the Lee-Carter diagonal. Well, this is basically just an application, really, of the Lee-Carter method on period data. What we do is we forecast mortality on period fashion from the age period Lexis diagram, and then we read the diagonals of this Lexis diagram to obtain the cohort information. So visually, again, we start from the age period Lexis diagram. We forecast mortality long way in the future. And then if we were interested in the mortality rates, let's say of the cohorts born in 1950 and 2000, well, we just take the diagonals across this age period mortality surface, and that's what we get. Okay, that's a possibility that is out there. However, there are some drawbacks in doing this. First of all, just by describing the method, it seems a bit strange to me that if we have age cohort data, why would one start from the age period one and then read things diagonally? Second of all, there has been a recent paper by Alison van Raalte and colleagues showing that it is a little bit dangerous to extract cohort patterns from the diagonals of period data, in that we might have some artificial fluctuations of our estimate that are basically driven from the fact that we are using a square of the age period Lexis diagram instead of taking the actual parallelograms that we should be using. Moreover, when we do this, we generate some mortality forecasts that are not useful for us. All the red area here is really not needed. And let's have a look, let's have a look at the forecasts themselves. Here I'm presenting two applications. We have Danish females on the left-hand side, males in England and Wales on the right-hand side. It's all log mortality. The top panels represent age, mortality developments over cohorts for age 35 and age 70, while the bottom panels is the age pattern of mortality for the cohort 1950 and 2000. And immediately it appears that if we look at the top panels, we can see a rather large jump of bias here, and also here, and perhaps also in the age pattern of mortality. So basically, we see that the first forecast point is really far away from the last observed point, which, in addition of not being very pleasing to the eye, it's also rather unreasonable, as we would expect that mortality doesn't change so abruptly, unless for COVID-19 or other shocks, of course. On the positive side, perhaps we could note that the age pattern of mortality, even for the 2000 cohort, is rather well, behaves rather well. We have this exponential increase in mortality, or in the log scale, linear increase corresponding to the well-known Gompertian increase of mortality over age. So if I want to summarize the Lee-Carter diagonal, it's a little bit inefficient. It has large jump of bias. There are some dangers of drawing core profiles from period data, but the shape of the mortality curve over age appears to be reasonable. So let's move to the first proposal that we do, that is a cohort Lee-Carter approach, which basically consists in taking our age cohort Lexis diagram and fit the Lee-Carter model on this cohort data. To do this, we need to modify slightly the estimation procedure, in that we cannot use singular value decomposition, as the matrix is full of missing data. But if we move to a Poisson setting, well, we can easily deal with that using weights. And importantly, when we do this, we are able to forecast mortality without the need of forecasting the cohort index, unlike the Lee Carter diagonal, where you also need to forecast the time index. So again, visually, here we have our age cohort Lexis diagram. If we simply fit the Lee Carter model to this data, well, we are able to obtain a complete mortality surface. These are the estimated parameters from the Lee Carter model on cohort data. On the left-hand side, we have the AX parameters. That is the standard shape of mortality over age. Central panels are the BX parameters. That is the rate of mortality improvement. And the right panels are the cohort index, which declines over cohort with some strong fluctuations at the beginning of the period because of little data. Let's have a look at the forecasts themselves. So Lee Carter diagonal is in blue, cohort Lee Carter is in red. We can see that the jump-off bias is reduced as compared to the Lee Carter diagonal, but it's still present, for example, here. And perhaps more worryingly, we can see that forecast over cohorts, they behave a little bit in an erratic fashion. But even worse, when we look at the age pattern of mortality, we see some departure from this linear increase in mortality over age with a sort of sinusoidal shape that is a little bit worrying and a little bit of a flag. So to summarize the cohort Lee Carter, we think it's much more efficient. It has smaller jump-off bias. However, it has erratic behavior along cohorts and sinusoidal shape over ages. That is why we think that the linear Lee Carter, it's a better approach. Basically, it's the same model as presented before, with the additional assumption that the cohort index follows a linear function. We still work in a Poisson setting. We still don't need to forecast the cohort index to complete the mortality experience of the partially observed cohort. And here are the results of the cohort Lee Carter approach. These were the previous set of parameters. And in orange, we see the linear Lee Carter ones. Alpha and beta, they look very similar to before, while you can see that our assumption of a linear cohort index. Okay, let's have a look at the forecasts themselves. Looking at the bottom panel, at the top panels, you can see that the jump-off error has been greatly reduced as compared to before. And when we look at the bottom panels, especially for the more recent cohorts, we can see that the linear Lee Carter follows much more closely the blue curve, the Lee Carter diagonal. So this exponential increase or linear increase in the log scale without this strange S shape. These are the prediction interval of Lee Carter diagonal in blue and the linear Lee Carter in orange for these two age groups. And obviously, by doing this, we can also, for example, have an estimate forecast of what will be cohort life expectancy for the 2020 cohort, and what will be the level of lifespan inequality for these populations. And you can see that the Lee Carter diagonal and linear Lee Carter have similar level of life expectancy at birth, but for example, they differ in the variability of their the distribution that is forecast. So to summarize, we believe that the linear Lee Carter provides a much more efficient way to forecast cohort mortality. It has minimal jump-off bias and reasonable shape over ages and cohorts. Now, the next steps of this project will be to formally test this statement with a bit more data and not being too subjective about it. So we started to perform some out-of-sample validation, and preliminary results suggest that linear Lee Carter is indeed more accurate in terms of both point forecast and prediction intervals, but we will have to do a lot more of this. One thing that we are not happy about is that the prediction intervals, you might have noticed that they widen rather slowly in the log rates and that they are very narrow for life expectancy at birth. So we are working to include extra Poisson variation, so over dispersion, either by using quasi-likelihood approaches or changing to a negative binomial distribution. We want to investigate what happens before. So you've seen that when we use cohort or linear Lee-Carter, we get not only the upper triangle, but also the lower one. So having a projection back in time might be useful for historical demography and so on. So perhaps this could be further investigated. And obviously, when the methodology is fixed, we will apply this to other population and investigate, for example, the relationship between cohort life expectancy and lifespan variability. Okay, I think I'm coming to the end of my time and the end of my talk too. I just have an extra slide, so bear with me just a couple of minutes more. I wanted to talk a little bit about what is my view for the future of mortality forecasting, or in other words, what lies ahead. What are the, in my view, in my eyes, the most prominent or important avenues for further research? So as I mentioned before in this talk, there have been a lot of extensions of the Lee-Carter model, and also new methods have been proposed in the last decades, including the one that I presented now. But there has been very little rigorous and comprehensive comparative research to try to find, to achieve a consensus on what is the best approach, best model in a particular situation. So I think this is worth to pursue. And in particular, it would be crucial to consider both model fit as well as forecasting accuracy with respect to both point and interval forecast. Another point that is worth keeping in mind is that the choice of the fitting period might have influence on the resulting forecast. So perhaps some work would be warranted here as well in order to try to minimize what is the effect of the fitting period on our forecast. And when we do out of sample validation, usually we take an average perhaps of different starting periods, and perhaps this could be done as well for the actual forecasts. When we talk about coherent forecasts, which I didn't discuss here, but basically it's an extension of mortality forecast where we try to forecast simultaneously different populations so that their forecasts do not diverge, but rather stay non-divergent over time. In this context, it's not still well understood how we should choose the standard population and what impact this might have. So future research might address this. Given the vast amount of models that are out there to forecast mortality, perhaps model averaging could be a fruitful avenue for further research. Indeed, preliminary studies or studies that have already been published seem to suggest that this is a potential good way to improve forecasting performance. And of course, last but not least, after having lived the last few years, it becomes quite clear that we cannot always think that extrapolating past trends can always be accurate. So trying to find a way to capture the effect of COVID-19 and potentially other, luckily, hopefully not future mortality shocks. But anyway, this could be an interesting line of research, I believe. Here are some references of the works that I've been citing here. Thank you very much for your attention, and I look forward to an interesting discussion with you.